Greetings. Today we are going to work on means testing. Today we're going to work on comparing means because we're going to take means from two different groups in some sense and compare them to one another. So we're taking two sets of data, but there's going to be a different kind of relationship to them when we talk about what was going on with correlation. Now, when we think about samples and populations, we're always trying to make this relationship. When we have the population, that's absolutely everyone that would fit into a specific group. But in the case of what we're talking about today, we're taking a sample of the population. And that's typically how research is done. A smaller sample is done. For example, you might have all third graders in the country, and you take a sample of third graders representative from certain classrooms. Now, the samples can be organized in different ways. Certain samples can be randomized. When we have randomized samples, you have more likely to have accurate results. So simple is just randomly taken. Stratified means the samples are organized in some way, and then you take some from here, some from here, some from here, and some from here. Systemic is in an organized way. Cluster, just take one group for some reason. Lots of times samples are non-random in nature. It does lower the trustworthiness or the reliability of the results. That's okay. Sometimes that's all we can do. We do what we can do. So samples of convenience are who can you get? Or quotas, you take a certain group. Purposeful, you target a specific group. Or snowball, you take some from here, and that informs the decision to take some from this group, which informs you to take some from this group, so on. So let's take a look at how we can look at levels of quantitative data and what kind of analysis would be appropriate for them. So here at the bottom, we have nominal level data. The chi-square analysis is a test. We'll do the chi-square analysis. We'll do non-parametric analysis later on, and the chi-square will be a test used for that. You might also have ordinal level or ranked data where you can have different types of analysis. And if you notice here, the Spearman's row, which is the correlation of ordinal level data. You can do the Wilcoxon test on that. And then when we jump up to interval level data or ratio level data, this is parametric in nature. Parametric over the course of a bell. Descriptives, mean, standard deviation, Pearson R. Because remember that correlations are descriptive, and then there are referential tests, the t-test, the analysis of variance, the analysis of covariance, and the factor analysis. In our course, we'll be working with t-test and analysis of variance. Those are the two levels we'll go to, and we'll discuss why you would choose one over the other. Okay. So key to selecting to compare means is to have some sort of experimental design associated with it. And experimental design requires you to have some sort of problem, and then you identify the variables, the independent variable and the dependent variable. So the independent variable is a factor that changes as a result, generally of experimental in nature, and the dependent variable is what happens as a result of that. So there are often levels of the independent variable, and you can have in a t-test two levels, group one, group two. Let's dissect a couple of research questions to better understand the independent and the dependent variables. So my first question is impact of instructional method, and the research question is, does project-based learning lead to higher student achievement scores than traditional instruction in ninth grade science classes? So this is a question where we can look and say, well, what is changing? And we have two things that change. We have the independent variable and the dependent variable. So one of the things that changes is the type of instruction, and that's what the title is, instruction method. And the two types of instruction are project-based learning and traditional instruction. So the independent variable is the instructional method. And there are two levels of this variable. Level one, traditional, and level two, project-based learning. The second part is what is dependent. So what depends on whether you get traditional or PBL? And in that case is student achievement. So the dependent variable is student achievement. I want you to notice something here. The word higher. Higher is a directional. So this implies a directional hypothesis, higher student achievement. If we said, does project-based learning lead to different student achievement scores, then that would be a non-directional hypothesis. So the research question, and we dissect it into the independent variable or the dependent variable. This question could be written in a different way. We could say, does the instructional method, uh, PBL, traditional, impact student achievement? Just a totally different way to look at it. Same question. This one reads out a little bit better because you can see the independent variable and you can see the dependent variable a little quicker. Let's go to another question. Look at another example. Okay, is there a difference in math self-efficacy between male and female middle school students? And by the way, we're defining what the group is in this case. So there's our research question. And then we're going to look for the independent variable first. What is changing? Male and female. Gender. So the independent variable is gender. Level 1 equals male. Level 2 equals female. Please notice on my level 1 and level 2 that these are nominal or categorical level data for the independent variable. Same thing happened here. Traditional PBL, this is nominal data. This is interval or ratio data. Same as this one. So the dependent variable, what are we finding out? What is dependent on male and female? Self-efficacy. So the dependent variable is self-efficacy. Some of the constants in this is we're doing this on middle school students. So middle school students is a constant in my experimental setup here, just as ninth grade science classes was a constant on this one. Let's go to the third one. So the research question is, do students show significant improvement in reading comprehension scores after participating in a 6-week literacy intervention program? So this is a timed situation. So the independent variable is time in some respect. We have a pre-post, or we have level 1 uh, before intervention, level 2 after intervention. And then what are we measuring? Reading comprehension. Dependent variable. I messed up my color pattern here, but that's okay. Reading comprehension. Okay. So looking at independent variables and dependent variables. For the t-test, the independent variable is always going to be categorical. Okay, so this will always be categorical or nominal level data. The dependent variable will always be interval or ratio level data. The t-test itself is used to determine whether two means are significantly different at a selected probability level. And of course, in education, we're always at p is less than or equal to 0.05. Sometimes you have to make adjustments for distribution of scores if the samples are particularly small. Now, this is really key because I think a lot of times people confuse the t-test and the correlation with one another. So correlation, you're always taking from the same sample, but you're taking something with two different measures. So where we have logical analytical thinking, IQ, and creativity. Those are the same sample from, so you take the same person, same sample, or per people, and then you do the measure of creativity, and then you do the measure of logical thinking or IQ. So when we have the same samples, uh, that would be something you can correlate. Does this variable relate to the other variable? That's different from a t-test where you have different samples, but the same measure. So for example, you have students who receive a special math intervention, for example. So you have a group of students who just get regular math instruction, and you have a group of students that get a specialized math instruction. Say, let's say it's illustrative math. And so we have different samples because they're different kids. These kids are getting one treatment, and these kids are getting a different treatment. So they're different samples, but we're going to measure them on the same thing. In my math example, maybe we're doing a math achievement test of some sort, like the ESPA math achievement at the end of the grade level. So different samples, same measure. So keep that in mind because people often confuse the correlation and the t-test with one another for purposes, and there are other couple of little clues we'll talk about too. And I'm going to do this through like a non-education example. And this is one that I like a lot because it's something I've done with students in the past, actually. So this is the mummy chog fish, and I just love its name, like mummy chog. Mummy chog are bait fish. They are found generally in estuarine waters, so they're found in salt marshes. You can find them in Long Island Sound. They are super, super hardy fish. They are very tolerant of stresses, and therefore you can use them for a lot of different things. So let's take these mummy chogs as an example, and we're going to take a look at how we could correlate or we could t-test. So let's say we go to Stratford, Connecticut. There's a marsh in Stratford, Connecticut. It's called the Great Meadows Marsh. It's a lovely place. It's off of Long Beach, and the marsh has these mummy chogs in it. And so if I want the same sample, so I catch a bunch of mummy chogs at Great Meadows Marsh, and then I say, I want to know what the relationship between their mass is and how long they are. And uh, and so then I do a correlation on that. And I did a linear correlation in my example here. I have an equation and I can figure out the R value. This is the R square, so we could take the square root of that. That's going to be almost zero point 0.9 by my eyeball guesstimation. Pretty high correlation between length and mass. Same fish, though, right? I took the mass of fish A and I took the length of fish A. And I took the mass of fish B and the length of fish B. And I did that over and over again to get my data samples. The same sample, I'm calling it the same sample because they came from the same location. In my t-test example, though, we'll just take one of those variables. Let's say like the length, because that'll be the outcome. But we're going to have two different samples. So we're going to take from Great Meadows Marsh and Stratford, but then we're also going to go down to Barn Island. Barn Island is right in Stonington, on the Rhode Island state line. It's a neat little marsh tucked behind Napattree Beach, where Watch Hill is. That's in Rhode Island. So it's right on the corner there. Super clean marsh. Um, Compared to Great Meadows. I've had students over the years test stuff in Great Meadows and Barn Island. It's a great comparison situation. So we do length of fish, and then this is the average. This is a means test. These meaned out at 72. These meaned out at 61, it looks like. Okay. Different samples, Barn Island, Great Meadows, same measure, length. Okay. Here's a different way to view that data. I did actually a box and whisker to show that too, so we can see these extremes. We got some outliers up here, so just a different way to look at the data. Now, there are basically two ways the t-test can be done. So you can have non-independent samples, which is called a paired test, or you can have the independent samples, which is different groups. So the t-tests are used for paired, meaning person one is going to be the pre and the post usually is the setup there, the pre and the post. So there's some set of matching. You can match individuals together. So we see if they did something, got an intervention, and look at it at the end. That would be the paired samples t-test. Does a significance exist between the means of two samples or the same samples at different times? The one that's more commonly used would be the t-test for independent samples, meaning classroom one, classroom two, or some treatment one, treatment two, intervention one, intervention two. That means the members of one sample are not related to the members of the other sample in other ways, except they were selected from the same population. Example, third grade classrooms. If the groups were randomly formed, we assume they are the same with respect to performance on the independent variable, the dependent variable. That's what we hope happens. It's not always the case, and we generally test that in advance, but we'll get into that later. So we're going to conduct the t-test. The plan of attack is as follows. You put your data in Excel, Google Sheets, XPSS, and you do similar data in similar rows, and then you do grouping categories in the adjacent row, and then you run the t-test. And I will do a separate video for you to show you exactly how that works. I was thinking about how to best summarize how we interpret t-tests without going through the idiosyncrasies and minutia of actually conducting the test, which will be done separately. So I think there are two key buckets we need to keep in mind. We have the test statistic and we have the significance. So the test statistic in the case of the t-test is the letter T. You're going to see other test statistics that we use as well. The F-test, the R you already done. The Pearson R was the test statistic. And those letters give you a value. And that value tells you about the calculation of that statistic. Ultimately, the decision is to determine where the significance is. And it's really that simple. Significance is the letter P, the probability. And when the letter P is less than or equal to 0.05, there is statistical difference, statistically different results. When P is greater than 0.05, there are insignificant and or no or statistical similarity is probably the better way to say it. So this is really key. You do your test statistics to calculate the value of what the stat is. You use the significance test and P to determine if it matters or not. So basically, to wrap up, what we want to say is the t-statistics p-value significant, p is less than 0.05, there is a statistically significance between groups. If it is insignificant, there is no statistically significance difference between groups. And that's really important to be able to say whether something is statistically different or similar, not just a comparison of the